Alright, so in this video we go over an application of the chi-square distribution to the goodness of fit test as a continuation of this chapter. So this test is used to determine whether an observed frequency distribution fits or confirms to some claimed distribution. In this case, the null hypothesis states that assumes that there is no significant difference between the observed and the expected value. So ultimately what we do in this distribution is compare observed values and expected values. And then the alternative hypothesis states otherwise, that there is a significant difference between the observed and the expected value. The test statistic and critical values, well, the critical values you already have an idea of how to find them using the chi-square distribution. But for the chi-square statistic will be the sum of the difference of the observed values minus the expected values squared, all divided by the expected value. Well, on an example, I'll show you how to use this formula, but ultimately you won't be expected to do it the long way. Actually, there is a really nice command to perform this test. In this case, O represents the observed frequency and E represents the expected frequency. Now, for the observed frequencies, because these are observations, these must be integers. While, well, expected, these are just some statistically calculated. Well, no need to be integers. And I mentioned this because when we on the examples that we are going to cover, we're integers. In the examples that we are going to cover in this lesson, all of them are going to be integers, but when you do the homework or if you run into situations in which these won't be integers, well, don't freak out if these are not integers. So again, the observed, because these are number of observations, we cannot observe half of an event. We observe one event, two events, three events, etc. But the expected, since are statistically calculated, well, those not need to be integers. Well, there are two cases to obtain the expected frequencies. Well, if all expected frequencies in case 1 are equal, then each expected frequency is the sum of all the observed. Expected frequencies are equal, the observed, divided by the number of total categories, in this case n, the total number of observations, divided by k, number of categories. In the case 2, if expected frequencies are not equal, we're going to do an example of each. So in this case, then each of the expected frequency is obtained by multiplying the sum of all the observed frequencies by the probability of the category, in this case E equals NP for each category. You will see. You'll see how is this going to be. All right. So in this case, let's see. Let's do one example. Oh, before doing the example, critical values come from table A4 using k minus 1 degrees of freedom, where k is the number of categories, and well, the number of categories minus 1. And the hypothesis test, in this case, you don't need to worry about left-tailed or two-tailed. The nice thing and really easy thing about it is that this is all right-tailed. Let's do one example. A police department released a number of calls for the different days of the week during the month of October, as shown in the table below. So from Sunday to Saturday, well, all this number of phone calls, notice these are all integers. All right, they are not. We don't call half a time. We call one time, two times, etc. The total number of calls in this case is n equals to 1442. We're going to need this piece of information to start doing the calculations. Use a 0.05 significance level to test the claim that different days of the week have the same frequencies of police calls. So in this case, the null hypothesis and the alternative hypothesis will be in the form of a sentence. So the null hypothesis will be that the police calls occur with the same frequency. That is, there's no difference in the proportion of calls for each day. Otherwise, well, we collect data to state that otherwise. If you look at the numbers differ for every day. And that's our alternative hypothesis, that at least one day has a different frequency of calls than other days. All right. So let's move on. Let's calculate the expected value here in this case. Well, in this case, this is case 1, in which we are going to divide the number of observations over by the what's this called? By the number of categories. In this case, 1442 divided by the number of categories, which in this case is 7, and as an answer I get 206. All right, I get 206 here. So let's see. So these are going to be the expected. So let's move on to the next page. So here we are going to have a little table in which we are going to repeat the observed values and the expected. The expected value was calculated in the previous page by adding all the total number of observations and then divide by the total number of categories, in this case 7, because there were 7 days of the week. So all I'm going to do is just repeat 206, 206, 206, 206, etc. Alright, let's use table A4 to find the critical value for this. Well, in this case, the degrees of freedom for this will be BF equals K minus 1, in this case, where K is the number of categories, in this case 1, 2, 3, 4, 5, 6, 7, because there are 7 days of the week. So 6 degrees of freedom. And it's a right tail test. Again, this one is easier to do as opposed to the other ones. So let's see. So we're gonna find chi-square critical with 0.05 and degrees of freedom 6. So 6 degrees of freedom, alpha of 0.05, this is going to be 12.592. That's going to be our critical value, 12.592. All right, how are we going to perform the calculation? Well, if you look back to the formula on the previous page, it's going to be the summation of the differences between observed and expected square over the expected. In this case, I decided to just show you the calculation here to avoid wasting too more time. If you want to pause the video and write all this down on your paper and then click play again, so you can watch the explanation to this. All right, now that you did that, well, so the statistic value, chi-square statistic, is going to be the sum of observed minus expected square over expected. So notice I have 1, 2, 3, 4, 5, 6, 7 calculations here. The first calculation corresponds to observed minus expected for the first piece of information, that is 157 minus 206. 157 minus 206 squared, and then divided by the expected, which is 206. I'm done with that part, plus the one that corresponds for the second day of the week. In this case, well, that's Monday. That's 207 minus 206, observed minus expected, 207 minus 206, quantity square over 206. And then I'm going to do the third calculation corresponding to Tuesday, 223 minus 206 over 206, the numerator square. And then for Wednesday, 244 minus 206, quantity squared over 206. And then for Thursday, etc. Thursday, Friday, and Saturday. And this might be a little bit painful to do, especially because when it comes to put all this in the calculator, so maybe a silly mistake on calculations for, for parentheses or something. So I'm just going to give you the answer here. So if you to put all this in the calculator, you should get 28.238. We're going to do this way easier than this using the graphing calculator with a command that I'll show you on the next example. So in this case, it's time to compare chi-square statistic of 28.238 is indeed bigger than 12.592. So in this case, well, our statistic value fell in the shaded region. So for this reason, we reject the null hypothesis because there is enough evidence to support it. So in other words, going back to the context of the problem, the null hypothesis wins. So we have enough evidence to claim that different days of the week had different frequencies of phone calls to the police department. All right. Otherwise, if the whole won, otherwise, well, then this data wouldn't have been significantly good to claim that there's that there is a different frequency for every day. All right. So let's do another example. And in this case, well, what do we have? A manufacturer of children's vitamins claims that its vitamins are mixed so that each batch has exactly the following percentages: 20% green, 40% yellow, 10% red, and 30% green. All right. So to test the claim that these percentages are incorrect, someone in the production line got 100 bottles of vitamins and they were pulled and the colors of the vitamins were tallied, and the results are in this table. So in this case, what do we have for this? Well, let's see. So we have n, a total number of observations of n equals to, if we add this together, we get, what's on my notes? 50-50 total. So 1149, 1948, 552, and that's what we get. Let me do the calculation again just to make sure. No, looks like I had different numbers here. This one was supposed to be not 140, according to my notes. This one was supposed to be 1401. All right, and 1401, and yes, we get 550. So not that number. Please correct that part. Okay, well, actually in your PDF file it'll be corrected. So 550. Now, in this case, well, so at alpha 0.05, determine whether there is sufficient evidence to conclude that the percentages stated by the vitamin manufacturer are incorrect. Well, in this case, well, the null hypothesis, it's going to be a little bit different. So in this case, we're not looking at a uniform distribution. That is, that everything occurs with the same frequency. In this case, P1, which is the proportion of green vitamins, is 20% or 0.20. P2 is 0.40, which is the percentage of yellow vitamins. P3 is 0.1, which is the percentage of red vitamins. And last but not least, P4, which is the proportion of green vitamins, which is 30% or 0.30. The alternative hypothesis is that there is some difference from the stated proportions. Well, in this case, how is this problem going to be different? Well, 1401. Okay, so in this case, as opposed to the previous problem in which we just added the total of observations and divided by the number of categories, that's because each category had the different, each category had the same expectation in proportion. However, in this case, it's not the case. In this case, well, there is some proportion. Let me get okay. There is some proportion for each green, yellow, red, and do I have another green? Do I have two greens? Maybe I should have used a different color. So green, yellow, red. I'm gonna put blue. Okay, the corrected PDF will have that blue. Well, in this case, we have 20% of this, 40% of this, 10% of this, and 30% of this. Well, so in this case, it's going to be a case 2 situation, a case 2 in which the expected frequencies are not all equal, and then in this case, multiply the expected, the sum of all observed frequencies by the probability of each category. Well, the probability of each category are going to be all these percentages in the form of decimals. So again, n equals 50-50. And in this case, to get the expected, that's going to be 50-50 times 0.20, which equals, in this case, 10-10. For the second case, 50-50 times 0.4, which equals 20-20. For the third case, 50-50 multiplied by the 10% for that category, that's 0.10. That's going to give us 505. And last but not least, 50-50 0.30 times 0.30. Oops, oh, this one's so messy. 50-50 times 0.3. And that's going to give us a total of, let's see, 15-15. So I'd better highlight these values just so you can see which ones are. So the expected, I'm going to highlight them with pink. And the observed are with pink, and the expected with green. Well, now, so we're not going to do this huge calculation anymore. So what are we going to do in this case? Well, so let's see. Let me clear my calculator first. Observe the values will be input in our calculator in L1, and expected values will be put in L2. So what are we going to do here? Well, so L1 will contain the observed values 1149, 1948, 552, 1401. L2 will contain the numbers we highlighted in green, or I boxed in green, 10, 2020, 505 and 1515. Okay, so I'm gonna quit and then I'm gonna do the test in a minute. So we need to find the critical value for chi-squared in this situation. Well, so degrees of freedom will be k minus 1, which is the number of categories minus 1. That is 4 categories, which is 1, 2, 3, 4. And 4 minus 1 is 3. And with alpha 0.05. Okay. Chi-square critical. And we're going to go to the table. So 3 degrees of freedom, alpha 0.05, that's 7.815. All right. So instead of doing that huge calculation as you saw on the previous page, we're going to go to our calculator. We're going to click Stat, Test, go down all the way until you find this. Well, it's not an X, it's chi-square GOF test. What does that mean? Chi-square goodness of fit, which is what we're doing in this section. Goodness of fit test. Click enter. And then observed values again are in L1, expected values are in L2. The degrees of freedom, be sure to put the correct ones. If you have already used this test before, well, just change the number. 2 in this case, change it to 3. Then go all the way down to calculate, and that's going to give us our chi-square statistic, which is 34.645. I'm going to round to 3 decimal places. So using chi-square GOF test, we obtain that chi-square statistic is 34.649. And in this case, well, time to compare. Notice this number 34.649 is a number way bigger than the critical, somewhere here. And in this case, we have enough evidence to reject the null hypothesis because we have enough evidence to support our claim. So in the context, well, with these numbers obtained from the 100 bottles of vitamins, well, it turns out that we had enough evidence that the distribution of each color from the manufacturer, oh, it's orange and not blue, never mind. The distribution of each, this is not the correct distribution, and in fact, there is a huge difference from the stated proportions. All right. So now we're going to do another very, very classical example in the chi-square distribution to determine whether a die is fair. Well, so if you roll a die, well, then you would expect to have a 1/6 probability to roll a 1, a 1/6 probability to roll a 2, a 1/6 probability to roll a 3, and so on and so forth, right, all the way to 6. So that'll be a fair die. But now in this case, well, a die was rolled 120 times, and the recording scores are listed here in the table. Okay, so the number of 1s, 17, the number of 2s were 20, the number of 3s were 29, number of 4s were 20, number of 5s were 18, and the number of 6s were 16. Well, n equals 120. In this case, as opposed to the previous example, they're not telling us that we would expect a 20%, I don't know, a 5% of 1s, a 35% of 3s. No, in this case, we want equal probabilities, which in this case is going to take us to case 1. in which all frequencies are equal. All frequencies are equal in order for the die to be fair. So the expected value for this situation would be that'll be n over k, the number of observations over the number of categories, which in this case is 20. So we would, if we roll a die 120 times, 1/6 of each category 1 through 6 would be 20 times in order to be fair. So the die seems to be fair for number 2 and for number 4. But in this case, the die seems to be biased towards the 3s and unbiased towards 7, towards actually 6, which is the lowest frequency observed. All right. Well, does the die seem to be fair? Well, use alpha 0.01 to determine that. And again, well, the hope is that the die is fair. Otherwise, the alternative hypothesis, so we are collecting data to to potentially and statistically conclude that the die is not fair. Well, we repeat the table of in the term of observe, in the sense of observed and expected. So 17, 20, 29, etc. And the expected we already calculated here is 20, 20, 20, 20, 20, and 20. So let's calculate chi-square critical for alpha 0.01 and degrees of freedom, in this case k minus 1, which is the number of categories, k, in this case 6, minus 1, which equals 5. All right, using the table. 5 degrees of freedom, alpha 0.01. The bound, or the chi-square critical, is 15.086. Okay, so in this case, we are going to calculate the chi-square statistic using chi-square GOF test. So now let's populate our list, and we're gonna, okay, let me go stat, edit. I'm gonna clear this list. I'm gonna clear this list, and I'm gonna put again observe the values in L1 and expected values in L2. All right, so 17, 20, 29, 20, 18, 16. And then over here, just repeat a bunch of 20s. All right, so let's stat, test, do the X, or not X actually, it's chi-square GOF test. Well, L1 is the observed, L2 is the expected, but the degrees of freedom, be sure to change it. I'm sorry about that. We still have the number 3 from the previous example. We need to change that to 5 for this example. Calculate, and the chi-square, what do we get? 5.5. I'm going to add 2 zeros just to have the same accuracy. And when we compare, look at this. The statistic value is less than the critical, a lot less than the critical. So for this reason, we don't have enough evidence. We fail to reject because there is not enough evidence to support our claim. So in this case, HO wins. So the die is fair. What happened here? Well, I mean, if you look at the 2s and the 4, it's fair for 2 and 4. But not too significantly unfair for 5 and possibly even 17. But it's kind of unfair for 3 and kind of unfair for 6. Also, well, it could have been as usual. You know, if we recall the types of error, it could have been a sampling error. Maybe we just, by luck, we got that distribution that is not representative of the fairness of the die in this case. Alright, so this is the end of this video. In the following video, we're going to go over the chi-square test for independence. I'll see you in the next video.